We're going to discuss finding the derivative of exponential functions in this section. As let's remember what an exponential function is. The idea exponential is really telling us that we have an exponent that is a variable or has a variable in it. So for instance, some examples of exponential functions. Some examples. Well, for instance, f of x is equal to 3 times e to the power x plus 5. And this exponential function, the base of the exponential function is e. And that is really referring to the value that the variable exponent is on. So you can see e is what x plus 5 is on, and x plus 5, of course, is a variable expression. Another example would be g of x is equal to 10 times 2x minus 3. Well, here the situation is the base of this exponential function is the number 10. So we're referring to the idea that when we have a constant that has some exponent on it that's got a variable in it, that's called an exponential function. Now, in this section, we're going to consider base e only. Now, so that means everything we see is going to have an e to a power in it. The book that you're reading may have other bases. We're just not interested in that, so you can kind of gloss over it. If you're interested in learning, certainly that would be a worthwhile project. But that's not what we're going to discuss in this section, and I don't believe you'll have any homework that requires you to know more. So we need to know how to find derivatives. So here's the first thing, that if f of x is equal to e to the x, then the derivative, that is f prime of x, and this is very strange, is also just e to the x. That's a very strange situation, of course. Another way for us to write this is that the derivative with respect to x of e to the x is simply e to the x. So both of those are stating the same thing. We're just stating it a little differently in the way it's been written down. Well, those are clearly something that we need to remember. But that alone, you can imagine, isn't really the whole story, because there will always be this question, what if the power on e is something other than x? Something other than just x. I'm going to write it as just x. Well, for instance, as an example, what if f of x is equal to e to the 3x plus 4 power, as an example? And that's not an unusual thing that we might see. Then how do we find f prime of x in this case? Okay, and it's not exactly what you might guess. So that's what we need to know about. And to do this, then we have to introduce the idea of the chain rule again. Now, remember last section, we saw the chain rule and a special case of it called the general power rule. Well, the chain rule acts differently when we have this situation. Let me state it this way. The chain rule version of what we see here, okay, and the chain rule version of these derivatives has to do with when our exponent is something other than just x. Let me write it this way. If f of x is equal to some e to some power that is an expression. So the power is something besides just x. Okay? Then the derivative of the function f is e to that same power. Okay, so that part kind of looks like above. It's e to the same power, but the chain rule tells us that then we have to multiply that with the derivative of that power. And that power, of course, is the expression. Now, another way we might write this, rather than using these words, would be that if f of x is equal to e to a power, and the power is some function in x. So that's the expression idea. Well, then in that case, okay, the way we would write this down is then f prime of x is e to that same power, but then we multiply with the derivative of the power. So we call that u prime in this case. And so this is the way the chain rule shows itself when we're talking about exponential functions. And this is, we might say, the chain rule version of it. So once again, we need to really be able to use this. And so on the next page, we'll begin to look at some examples. Well, you can see our first example is that we have a function f of x equal to e to the negative 3x power, and we're to find f of negative x. Now, I'm going to write down a couple of notes before we do this, and I'm going to remind you of the chain rule version. And the chain rule version of the derivative that we looked at from the beginning is that if f of x is equal to e to some power, okay, then the derivative of f of x is e to that same power times the derivative of the power. Now, another way to think about this is anytime the exponent on e is more than x alone, we must use the chain rule. And that's what's above. We must use the chain rule. I'm going to keep reminding you of this. That's the chain rule idea. I'm going to keep reminding you of this as we come across these problems. So in our function f here, we see that the exponent on e is not x. It's negative 3x. And so since it's negative 3x, we have to use this chain rule version. So here's the way that goes then. F prime of x is e to exactly the same power. The power on e does not change. What we have to do, though, is multiply with the derivative of the power that is on e. So we have to multiply with the derivative of negative 3x. And of course, it doesn't take us a bit of time here. We remember the derivative of negative 3x, of course, gives us a result of negative 3. And then we would simply rewrite that as negative 3 times e to the power of negative 3x. So there's the derivative that we were looking for. Okay, well, let's look at the next example rather quickly. And in this example, find, we'll say g prime of t if g of t is equal to e to the negative t. So I changed things a bit here. One, I'm using a new function name, and two, I'm using a new variable name. instead of f, we're using g. Instead of x, we're using t. And I guess I need to mix it up once in a while. Well, the chain rule version really isn't so much about x's and f's. It's the concept of e to a power. And if we have e to a power other than the variable only, then we have to use the chain rule. So if this was g of t is equal to e to the t, then that wouldn't require the chain rule because we have negative t, not just t. See, negative t, not just t, requires the chain rule. And that means we have to multiply with the derivative of the exponent. So we're kind of back to the same thing. This is making clear that we understand we're not always talking about x's. Okay, so to find g prime of t means we have e to exactly the same power. The power doesn't change, but we multiply with the derivative of. Now let's be careful here as well. I'm so used to writing d over dx, but the variable's not x this time, it's t. So we're saying d over dt, and this reads the derivative of, and we haven't written the of yet, okay, the derivative of with respect to t. Now what we're taking the derivative of is a negative t, and we're taking it with respect to t. So the t down at the bottom is the variable name. Well, the derivative of negative t is just negative 1, isn't it? So we would have g prime of t is equal to e to the negative t power times negative 1, which would simply be negative e to the power negative t. And so that's the result in this case. And just as a reminder then, we could have written this differently. I could say, what's the derivative with respect to x of e to the negative x? And it would be the same procedure, except now we're talking about x's instead of t's again. The result would end up being the same, it's just with a different variable name. We would have the negative of e to the negative x because we have the exponent's not x, it's negative x. We have to multiply with its derivative as well. So let's move to yet another example, I believe, on the next page. Well, you can see here is our next example about finding derivatives of exponential functions. Stated a little differently yet. Find the derivative of y with respect to x if y is equal to 6 times e to the power 5x squared minus 2. So notice here that this is certainly more complicated. We have the 6 that's in front, and our exponent, 5x squared minus 2, is certainly a more complicated exponent. Now, here's what I need you to recognize, and that's the big issue about a lot of these problems, is we've got to recognize the approach we take. And we've got to understand what it is we're trying to do. And I want you to remember the basic rule that said to find the derivative of some constant times a function. And at the time, that didn't seem very important, but now we're going to see it becomes more important. The derivative of some constant times a function is the constant times the derivative of the function. And we did that with something like 5x squared, and that was the 5 times the derivative of x squared. Okay, but here, of course, it plays out a little differently. Well, in this case, the constant is the 6. So we have 6 times this function, which is an exponential function. So we need to recognize when we're dealing with something like that on the way we approach the problem. So we start out this way, then, the derivative of y with respect to x in this case, of course that's the derivative of this expression or this function 6 times e to the power 5x squared minus 2. Now, as we just discussed, when we're taking the derivative of a constant times a function, then it's just the constant times the derivative of the function. So it just allows us to concentrate on finding the derivative of something that's not quite so complicated. Now, that's the derivative of an exponential function. And the power in this case on the e is not x alone, and so we have to use the chain rule. And so remember what we do when we have the derivative of an exponential function. It's the exponential function, that is, it's e to the same power, exactly the same power, but then we have to multiply with the derivative of that power. And of course, that power is 5x squared minus 2, and so the derivative of that power would be, what, 10x? So this ends up being 6 times e to the power of 5x squared minus 2, and of course, that derivative ends up being 10x. And we see this product we can simplify. We have the 6 times the 10x, and so we can write that, of course, as 60x, and then times e to the power 5x squared minus 2. So this is the resulting derivative of the function we were first given. Let me point out before we go to the next problem that the chain rule for these exponential functions works all the time, even in the simple case of f of x just being e to the x. So let me point that out to you. It just is so simple here we don't need the chain rule, but if we were to use the chain rule, we would calculate the derivative by saying it's e to the power times the derivative of the power. And in this case, since the power is just x, the derivative of course x with respect to x is just 1. So we'd end up with e to the x times a 1. And of course, that's just e to the x. So the power rule actually, the chain rule actually works, but it's just something we don't need if the exponent is x alone. So we'll do one more derivative, one more example in this introduction to exponential functions, and then we'll have another part, a part 2. But on the next page, we'll look at this next example. Okay, here we see the next problem. Our function is y equal 3 times e to the 5x plus an x squared. And we're to find dy dx, or the derivative of y with respect to x. Now this one also has a twist that's a little bit new, and so we're mixing things up. We know how to find the derivative of exponential functions, but what happens when we have other pieces involved? And so what I need you to recognize this time is, because of that plus sign right there, that we have to consider this as a sum of functions. We haven't run into this kind of thing except with polynomials when we took the derivative of each term. See, that was one of the basic rules again. One of the basic rules for derivatives. Another basic rule is, what do we do when we have the derivative of a sum or difference, but in this case it's a sum of one or more functions? Well, we simply take the derivative of each of the functions separately and add those results together. So it's just the derivative of the sum is the sum of the respective derivatives. And so in this case, that's our situation, is that we have the function 3 times e to the 5x is one function, and x squared as the other function. We're adding two parts together. So to find the derivative of y, the derivative of y with respect to x, that's simply the derivative of the first function, which is 3 times e to the 5x, plus the derivative of the second function, which of course is x squared. Now, in the first case, we're needing to deal with the fact that we have a constant times e to the 5x. And so when we do that, if you recall, that's the constant times the derivative of the function. So we may not write this down all the time in this fashion, but I hope it's helping us understand how we approach this. And of course, the derivative of x squared we know is just 2x. So we go back and look at this derivative of e to the 5x, and we remember, oh, well, this is e to a power. And so we have to use the chain rule version of the derivative of e to a power. Here's our 3 out here. The derivative of e to the power is e to the same power, but then times the derivative of the power itself. And of course, the derivative of 5x is 5, so we have a times 5, and then don't forget plus 2x at the end. And then we look what we have at that first term. We've got a 3 times a 5, or 15, times e to the 5x, and then plus 2x. And so that's the derivative in this case. And we had to recognize from the beginning that we had to approach this as the sum of functions, and to find that derivative, that's the sum of derivatives. Well, this is the end of the introduction, and we'll have a part 2 that will introduce a few more problems that are a little more complicated, and maybe even some word problems. Okay, that's all for now.